Hi guys, I will go over the simple linear regression questions in the sample final that I've shared with you in the auto class. And the first question seems as 50 points. I predict that in your final you will get a question like that. So let's start with the first part. Here we need to obtain the least squares estimates of beta 0 and beta 1. Here you can just use the formulas for beta 1 hat and beta 0 hat, which are things you should memorize. The beta 1 hat is basically summation of small xt yt over summation of small xt squared. Okay, now xt represents here the explanatory variable, which is g, and yt represents the explained variable, l. Here we have all the data, all the calculations for us. So the summation of small xt yt is here. We can just write it. And the summation of small xt squared is given here. You can just write it. And by using your calculator, you just calculate the beta 1 hat. And for the beta 0 hat, we have the other formula, which is y bar minus beta 1 hat times x bar. You can find y bar by dividing the summation of y's by the sample size. Here, we have the sample size as 25. And summation of y's is summation of l's. Here you can see it. If I divide it by 25, the sample size, I can get the y bar. And for the x bar, we can do the same thing. Our x's here are g's, and summation of g's is given here. If I divide this by 25, I will get the x bar. And for the beta 1 hat, we have already found it in the previous part. We just put the values instead of the formula, and we get beta 0 hat. Now we can write the model in its values like this. You see beta 0 is minus 0.54 plus our beta 1 comes here and gt. So LT hat is equal to minus 0.54 plus 0.48 gt for the t values from the year 1988 to 2012. In the second part, we need to calculate the coefficient of determination, which is r squared. And from here, we can also find the correlation coefficients, because we know that r squared is the square of correlation coefficient. Now, instead of r squared formula, which is 1 minus ut hat summations over the difference between fitted values and actual values, you can just use the correlation coefficient formula. You see, correlation coefficient formula is normally summation of xt yt over in the square root, summation xt squared, summation yt squared. Now, if you take this, take the square of this formula, you will get r squared. So in order to calculate the r squared, we just wrote the squared version of the correlation coefficient between x and y. Here we have summation of small xt, small yt. We can see its value here. And in the denominator, we have summation of xt squared and summation of yt squared, which are given in the question as well. We have used them in the previous part as well. So you will just put the values and calculate. You need to know the formula for the correlation coefficient. And by taking the square of it, you can find the r squared. So we have found the r squared values, which tells us that this model tells us that the x values, the g values explain the change in L by 59%. Okay, so by taking the square root of it, we can find the correlation coefficients. You see? And that's all for the part B. Now, to find the variance of the model, we know that the variance of the model is sigma square, and sigma square's formula is summation of ut hat square over sample size minus 2. Here is the formula. And summation of ut hat square can be found from this formula. It is summation of yt square minus beta 0 hat summation yt minus beta 1 hat summation xt yt. Again, we are putting the values instead of the, the y's, xt's in the formula. And we're finding the summation of ut hat square here. By dividing it by t minus 2, we are finding this sigma square, the variance of the model. And in the part D, we are finding the variances of the coefficients. Okay, beta 0 hat and beta 1 hat. These formulas include sigma square hats, which we have found in the previous part, but some extra terms. For example, the variance of beta 1 hat is sigma square over summation of small xt square. And the variance of beta 0 hat is sigma square times summation of large xt square over t times summation of small xt square. You need to know the formulas for the variances of beta 0 hat and beta 1 hat, because you will need them in order to test the significance of beta 0 hat or beta 1 hat, or in order to construct a confidence interval. So here we have the formulas, and we are putting values for summation of large xt square. We have this, and our t is 25, and small xt square is given. And here we are doing the same thing and finding the variances of beta 0 hat and beta 1 hat. Now, as I said, here we need to construct a 95% confidence interval for beta 0. In order to do that, we need to know the estimated value of beta 0 first. We have found it in part A. Beta 0 hat is negative 0.54. Okay, so first we write it 54. Okay, and the confidence interval is this estimated value plus and minus the t value times the standard error of beta 0 hat. We have found the variance of beta 0 hat as 0.075. So by just taking the square root of it, we can find that standard error of beta 0 is 0.27. And the t value has this degrees of freedoms. First, we have sample size minus 2, which is 25 minus 2, 23, and alpha over 2. Our alpha here is 5%. Okay, so alpha over 2 is 2.5%, which is 0.025. By looking at the table, we can see that this t value is 2.069. And we calculated that our standard error for beta 0 hat is 0.27. And we have the estimated value, so we can construct the confidence interval. Subtract t times standard error of beta 0 hat from minus 0.54, then add these terms to minus 0.54, and you get a confidence interval. In the part F, we have a t-test we are testing that if slope coefficient is statistically significant or not. I will come to the economically significant part later. First, we are writing our null hypothesis, which is H0 is that beta 1 is equal to 0. It means beta 1 means nothing. And the alternative hypothesis is H1, which says that beta 1 is not equal to 0. If you see that kind of test, like something is something in H0, and in H1, you have something is not something. You will have a two-tailed test, okay? And the decision criteria for a two-tailed test is that first, you write the estimated version of the thing you are asked to test, which is beta 1 hat, okay? Beta 1 hat. And you subtract the thing the null hypothesis says that it is beta 1 hat. Okay, this is 0. So beta 1 hat, the estimated number, this is actually a value, minus 0, since the test tells us that, over the standard error of beta 1 hat. Okay, and we have found it. We have found the variance of beta 1 hat as 0.0072. By taking the square root of it, we can find the standard error of beta 1 hat. And here we can see the value and divide this thing by this. Okay, and here we are finding the value as 5.76. Now, if this value is greater than the corresponding t-value, which is t23 0.025, then we reject the null hypothesis. If this is greater than t-value, we will say that no, beta 1 is not 0. Okay? So here we see that 5 is greater than 2, so we can reject it and say that beta 1 is statistically significant. And the economic part, here we can see that G is employment growth, okay? And L is the average GDP. So if employment growth is increasing, there should be an increase in average GDP. This is what economic theory tells us, that there is a relationship between employment growth and average GDP. So by economic theory, we can say that these two are related. So yes, the slope coefficient is economically significant. That's all you will have to say. Now in part G, we need to test whether the regression model as a whole is significant. If we test the model as a whole, we are using F-test. Our null hypothesis is beta 0 and beta 1 is equal to 0. They are both equal to 0. And H1 here is at least one of them is not 0. Okay? To test this, we have this formula. This is our criteria, like this one. Okay? In the previous part, we compared this thing with the t-value. Now, we are comparing this thing with the f value. Now the formula says that we need to calculate r squared over 1 minus r squared times t, sample size, minus k, number of restrictions in the null hypothesis, which is 2 here, beta 0 is 0, beta 1 is 0, okay, we have 2, minus 1. This comes from the formula, this one. And divided by p. P is number of parameters. We have 2 parameters. Our model includes beta 0 and beta 1. Okay, so here both k is 2 and p is 2. We put the values in the formula and we are finding that our decision criteria is coming up as 16. So if this thing is greater than the corresponding F value, which is something you can find from the F table, the degrees of freedoms are, first of all, you need to find it with the 5% alpha value, because the question doesn't give us any information about the alpha value. So you can just assume it is 5%. And the number of, and the degrees of freedoms are 2, number of parameters, and 23. Okay. Now, if you look at the table, you will see that this F value is smaller than 16. I haven't looked it yet, but the 16 is a large value, okay? So our finding in this part is greater than our F value. So we can reject the null hypothesis and say that beta 0 and beta 1 is not are not both statistically insignificant, okay? Here we can say that the model as a whole is statistically significant. And in the part H, we have another test. The null hypothesis tells that beta 0 and beta 1 is equal to 1. And as you can predict, the H1 is beta 0 plus beta 1 is not 1. We are writing the decision criteria again. First, we are writing the estimated values, beta 0 hat plus beta 1 hat, minus the value the null hypothesis tells us, which is 1, okay? And in the denominator, we have the standard deviation of beta 0 plus beta 1. Here, the standard deviation of beta 0 and beta 1 hat is found like this. You sum the variance of beta 0 hat and variance of beta 1 hat and subtract the covariance between them. When you do that, you will find the variance of beta 0 hat and beta 1 hat as this. And taking the square root of it, you will find that standard error between them is 2.28. So you will write the denominator here. You will write this. And you will compare it with the corresponding t value, which is 25 minus 2, 0.025. Since you know that this thing is 2 point something, okay? Since this 3 minus 3 in absolute terms is greater than the t value, we can reject H0. So beta 0 plus beta 1 is not 1, okay? We cannot, we can reject the null hypothesis here. In the part I, we have the prediction issue. Here our data includes values until 2012, okay? But now we are dealing with 2013, which is future. Now, this is a simple one. We are predicting the level of L when G is 2. Just ignore this percent thing because everything here is in percent already. Okay, so you are just writing the model you have found in the first part of this question, this 50 points question. You see, at the very beginning, we have found our model. You see, here it says that you know the GT in 2013. What will be the LT? Okay, this is very basic. Okay, so we are putting 2 instead of G and finding the L. That's all. And in the part J, we are obtaining the least square estimate of the prediction error variance. Now, this thing has a formula like this. It is different from the error variance, the variance of our model, because, you know, it is future. It includes some other slight modifications. So here is the formula. First, we are writing the error variance, sigma square, which we have found in the previous part. And then we have another part, 1 minus 1 over our sample size plus the predicted difference in x's and x's means square over summation of xt square. Here, this thing is like the predicted x, the future value of the x minus x bar, okay? The meaning of this is this. So you can find this by this, 2 minus x bar, okay? And we have already found the x bar in the previous part, so we can just write this. 2 minus 2.81 is minus 0.81. Okay, so we are putting this here. And the rest of it, you know, the summation of xt squares is given in the question as well. So we are calculating the prediction error variance as 0.46. Now in the part K, we are constructing a confidence interval for a future value for L 2030. Since this is a future value, it is not in our data set, we will use the prediction error variance here. Okay, first we need to estimate the L 2030, right? And to do that, we are using our model. Here is our model. We are writing 2 instead of G and finding the estimated L value first. And then, you see, this is estimated L value, okay? It is calculated here. You can do it yourself, but this solution doesn't include the calculation of it because it is simple. You will just put 2 instead of G here and find the estimated value of L. And then, what are we doing? The estimated value plus and minus the t value times the standard error, right? Now the standard error here is the predicted standard error, okay? Here we have found the prediction error variance. So if you take the square root of it, you will find the prediction standard deviation, right? Here it is found as 0.68. So, and the t value, you know, it is the same. It is t25 minus 2, comma 0.025 alpha over 2, you know. Alpha is 5%, so alpha over 2 is 2.5%. So t value and the standard error of the predicted value. That's all. T value is given. We have used it in the previous part, so we know that it is 2.069, and the error prediction is counted as 0.68. So that's all. I hope you can do it in your final. And let's go to part L. Now we need to test the significance of the prediction error, okay? First, we need to predict the error, okay? The error prediction is the actual value of the future L minus the predicted value. Now we have predicted it as 0.43 here. But now the question tells us that it is 1.5. So we need to measure the difference between the actual value and predicted value. Here we can see it is done, and it is 1.06. Now to test it, first we are writing this value, you see. We write 1.06 and then we subtract the null hypothesis value, which is 0, and divide it by the standard error of the thing we are testing, which is found in the previous part, right? We have found the prediction error variance here, and by taking the square root of it, we have found the standard deviation of it. So we are using the standard deviation that we have found here. 0.68, okay? And this is our, this is the thing we need to compare with the corresponding t value. Here, we are seeing that this comes up as 1.56. Now, we know that T23, 0.025 is 2 point something. So this is not greater than this. So we cannot reject it. Since we cannot reject it, we say that prediction error is statistically insignificant. That's all. Now, here we have an interpretation. We are just commenting about the model, okay? Now, in this question, we have found R square, right? R square is not small. It is not bad, 59%. Also, we have tested the significance of the model as a whole, and we said that the model is significant as a whole. Also, we have tested the significance of beta 1 hat, and we concluded that it is also significant. Now, here it is said that the intercept term, the beta 0, is statistically insignificant. We haven't tested in the previous part, but you can test it, and it will come as insignificant because its value is too small, and its variance, it was considerably large. So that will come up as insignificant. So you can say these things in the interpretation of the model. That's all. Now, in the second question, we have a simple linear regression model. Okay. Now, we need to show that the estimators beta 0 hat and beta 1 hat are unbiased. First, we are writing the formula of beta 1 hat. Okay, this is summation of xi minus x bar times yi minus y bar over summation of xi minus x bar squared. This is also equal to summation of xi minus x bar times yi over summation of xi minus x bar squared. So this part can be turned into this part. These two things are equal to each other. You can see how it is done by the notes I have uploaded in the previous week. These two are equal to each other. You can see it by separating and multiplying the terms one by one. And you will see that some things are canceling each other out, and you are left with this thing. This is also equal to this one. Okay, now here, we need to take the expected value of beta 1, right? So expected value of this. Now we know that the summation of xi minus x bar over summation of xi minus x bar squared, these things are non-random. These are x values that we know. They have some values, like x1 is 2, x2 is like 6, okay? X's are non-random in simple linear regression model. So you can take these things outside of the expectation. Here, we have done it. We have written expected value of beta 1 hat. It means expected value of summation of xi minus x bar times yi over summation of xi minus x bar squared. And in this expectation value parenthesis, we took the x's outside of the expectation value, you see? But we didn't take the y's outside because y's are random. Why? Because y's include error term, and error terms are considered to be distributed normally from Gauss-Markov assumptions. So these y's are random actually, but x's are not. Now, after we have done that, we can write beta 0 plus beta 1 xi instead of yi. And from here, we can separate these things. You see, first we can write beta 0 times summation of xi minus x bar over summation of xi minus x bar squared plus beta 1 xi times this thing. You see? This is the expectation of beta 1 hat. And now you can see that this term is 0. Again, you can see how it is done by the notes I have uploaded in the previous week. And this term is 1. Again, you can see it from there. So we have expectation of beta 1 hat as just beta 1. So we can say that beta 1 hat is an unbiased estimator for beta 1, since the expectation of it is equal to the parameter. And for the variance of beta 1 hat, we have this formula. Again, you can see from here that variance of beta 1 includes some constant terms and yi. What do we do about variance? We take the constants outside of the variance parenthesis as squared, right? Like 3y, variance of 3y is 9 times variance of y. This is what we have done here. And variance of y's are sigma squared. We know that from the assumptions of Gauss-Markov. Here, we are seeing the squared version of this term with x's, you see? And if you take the square of this x terms, you will see that it is equal to 1 over summation of xi minus x bar squared. You can see how it is done in the previous note as well. So we have found variance of beta 1 hat as sigma square over summation of xi minus x bar squared. Now let's get to the beta 0 hat. We are writing the formula of beta 0 hat again. And here we take the x's outside of expectation parentheses, as always, because they are not random. And also here, x1 bar is just a constant number, right? So we took it outside of the expectation parentheses, and we are left with expectation of yi bar, y bar, you can say, minus x bar times expectation of beta 1 hat. Here, if you write the formula of y bar, which is beta 0 plus beta 1 x bar, and here you will have x bar times beta 1, because expectation of beta 1 hat is equal to beta 1. And these terms will cancel each other out, and you are left with the fact that expectation of beta 0 hat is equal to beta 0. About the variance of beta 0 hat, again, we are writing the formula of beta 0, y bar minus beta 1 hat times x bar, and we are separating things up. Variance of yn, y bar, plus the square of the constant term, x bar squared, times variance of beta 1 hat, minus 2 times the constant term times the covariance between y and beta 1 hat. Now here beta 1 hat, as you know, is this summation of xi minus x bar over summation of xi minus x bar squared, and we have a y here, right? So instead of this beta 1 hat, I can write summation of xi minus x bar over summation of xi minus x bar squared times yi. So we have the covariance between y bar and something times yi. And y bar also can be written in terms of yi. So you are just trying to find the covariance between yi, summation of yi over n, and some x values, some non-random values times yi. And as you all know, the covariance between yi, yj is 0. There is no correlation between them. They are random. So here you can say that the covariance term will cancel, and you are left with variance of y bar plus x bar squared times variance of beta 1 hat. We have already found the variance of beta 1 hat. So you can write it here, yeah, sigma square over summation of small xi's, okay? And x bar square just stays here. We can't do anything to it. And variance of y bar is sigma square over n. Y, you know, variance of y is sigma square. Let's write this. Variance of y is sigma square. So variance of summation of yi's over n is equal to 1 over n square times n times sigma square. So these cancel each other out, and we are left with sigma square over n. Okay, so variance of beta 0 hat is found as sigma square over n plus x bar square times variance of beta 1 hat, which is given here. And you know, by taking the parenthesis here, this is sigma square. In sigma square parenthesis, you can write 1 over n plus x bar square over summation xi minus x bar square. This is the variance of beta 0. And as a summary, it's just, he just revoked the expectation of beta 0 hat is equal to beta 0, and variance of beta 0 hat is equal to this term, sigma square times blah blah. So that's all the simple linear regression part in the sample final. Let me check the other questions and ask the teacher if you need to study again for the, you know, the midterm topics. I don't think you will face these topics, but let me ask the teacher. You can study on yourself for now. Okay.